Today we have Dr. Stephen Woltering with us, who has studied, and I will pronounce this wrong, so he will correct me, at a university in Amsterdam. Amsterdam. What's the official name?
De Vrije Universiteit in Amsterdam. But,
Beautiful.
you did
That's
great.
beautiful.
Yeah.
Um, with the Department of Biological Psychology, he moved to Canada to pursue his PhD at the University of Toronto in developmental neuroscience, after which he accepted a faculty position here at Texas A&M University. He is currently an associate professor in the Department of Educational Psychology, where he directs the Neurobiological Lab for Learning and Development, or the NLD. The NLD is aimed at bridging the fields of education, neurobiology, and psychology to make better decisions on how we learn. Dr. Woltering's research focuses on the development of individual differences in and the treatment and training of executive functions. He has published several articles in top journals in topics ranging from working memory training in college students with ADHD to neural correlates of responsible inhibition in children with antisocial behavioral problems. And he recently focused on how sleep affects the executive functions and is one of the first scientists at A&M examining the brain during sleep. So without further ado, I will turn it over to Dr. Woltering.
Thank you very much. I'm going to try and see if I can share my screen. And does it work? Can you all?
It does. It's perfect.
Wonderful. So this is my son. I also have a newborn, although he's now almost 2 years old. But this picture was taken, I think, when he was about 1 year old. And as you may know, about any of you who have children, they do sleep a lot. And that also is something very interesting because it tells you that sleep is a very fundamental property especially for the development of the brain as well. What you also learn, obviously, as you're being a parent, how important sleep is for your own emotional and cognitive functioning, right? So if you're constantly being interrupted and you're going on sleep that is less than 6 and 5 hours a night, you'll start to notice all these deficits. Also, pointing to the fact that, this activity of sleep is very important. Now, you've mentioned I'm part of I founded the Neurobiological Lab for Learning and Development. So we kind of look at behavior and humans as part of our biology. And if I look at sleep from an evolutionary perspective, it's an absolutely very dumb thing to do, right? Imagine about you all. If you live until 90 years old, you're probably going to spend 30 years of that sleeping, not conscious, you're not finding mates, you're not seeking food, you're not making money, all these things that you think you're active and productive, that you perhaps think are meaningful in life, you're not doing when you're sleeping. And so sleep is very likely, performing a very fundamental aspect of life. Now, we see it also in a lot of different species, and we'll talk a little bit more about that later, what the actual function of sleep is or why we sleep, because up until recently, a lot of sleep scientists weren't even sure or didn't really even agree on what the reason was. Now, you may notice with my son that he has this weird helmet on, and you may think coming to this talk about sleep by a neuroscientist that I'm measuring my brain activity of a child, but this is actually for a different condition for his skull. Has nothing to do with it. But I would be crazy enough to measure his brain activity during sleep. I have what's called a polysomnograph in my lab. This is what it looks like. It looks a lot less elegant than the helmet that my son is wearing. And, the hope is that in a few years from now, we won't be needing all these wires and puha anymore. And we'll be able to have wearable devices that have similar, if not better, reliability. Currently, this is the gold standard of human sleep research. And so what you can do with these kinds of toys is obviously a lot of this is lab-based. So you have to get people into a sleep lab to do this kind of work. And then you have, you can do EEG, measuring brain activity, electrical potentials from the scalp, electrocardiograms, electromyograms, so measuring like muscle activity, electroculograms, so you measure movements of the eyes. oximeters, respiration, breathing, et cetera, et cetera. So we measure a lot of different things when people come into our sleep lab and they're falling asleep or for example taking a nap. And what you'll see on the EEG when people are asleep is, yeah, in my opinion, just truly amazing. Like I have recently, well, I have to say relatively recently gone into sleep research, but I've been focusing most of my career on trying to understand brain activity during cognitive function, executive function, like emotion regulation. What does the brain do during that point? And most of it is all when people are awake. And when people are awake, you see these kind of squiggles on your screen. You can see the one on top there. It has a particular rhythm. So you have to imagine that when you're a neuroscientist and you do electrophysiology, what you're mostly interested in is activity like oscillations is what you're seeing. You're seeing these rhythms of the brain. So there's these brain waves. Sometimes these brain waves go very fast. Sometimes they go very slow. Sometimes they're all mixed together. Sometimes they go very slow and very fast, very high and stuff. So there's all these brain waves. And what you see during awake, we call that mostly dominant by beta activity. It's a particular frequency, a particular rhythm that you see over there. And if I were to ask Madeline, for example, oh, can you do like a difficult puzzle task? And then can you think about politics? And then can you think about sleep, for example? I cannot see anything on the screen that will tell me anything about any cognitive activity that goes on. It's all this beta activity. I have to do very specific analyses for me to find out what mental state you might be in. It's very difficult for me to do. Now, during sleep, that kind of is thrown out of the window. So let's go through what happens and what you'll see in the EEG and some of these measurements when people are falling asleep. So the first thing is stage one sleep, and what you'll see is that your brain waves slow down a little bit. Call that sort of alpha waves start to occur. It's a sort of the first stage of sleep, and if I were to wake you up from that stage, you'll be like, oh, I was just falling asleep, right? You're not really cranky or anything, but you're just in this half-wake sleep kind of slumber where you're in. Now, from stage one, you go to stage two sleep, and this is where some weird things start to happen. Here, the waves get even slower. So we call them theta waves. So they have a particular, even a lower frequency. But what you also start to see, and I have a picture of those at the top here, K complexes and sleep spindles. Now, K complexes are the largest electrophysiological things that I don't even need to put any analysis on it. I can just see them to analyze them. In these K complexes, we don't know exactly what they're doing. They may be generated by the thalamocortical neurons that we see that sort of make sure that if you hear a sound that you're able to wake up, and that's sort of what we think they have to do. What we also see is these short bursts of activity, and you can see them on the very right top there, and we call those sleep spindles. Now, sleep spindles, we do now know from research that they're very much related to memory encoding. Having a lot of sleep spindles is related to having a good memory, for example, being able to remember things that you've learned from the day before. And so we did not see any of those during stage one, but as soon as these start to show up, scientists code them as now you're in a stage two sleep. If I am going to wake you up from a stage two sleep, you're going to report that you're asleep. I mean, you're really asleep. I may have to shake you a little bit. You'll wake up, but you'll report that you're asleep. There's other things that happen. Your heart rate starts to decrease. Your breathing rate starts to slow down. The temperature of your body gets a little lower. There's all these other physiological changes that kind of go along with stage two. Now, after stage two, you go into what we call deep sleep or slow wave sleep, as it's also called. Now, American Society for Sleep Medicine is now combined stage three and four, but maybe in your textbooks from high school, you might remember four stages. Doesn't matter. The characteristics here is that what you see here on the screen, what I see on my screen when people are in deep sleep is like incredible. There are these, for a neuroscientist, it's like unheard of. If I were to see these kind of patterns when people are awake, you're probably in a coma. You should be rushed to a hospital. So these are extremely slow. We're calling delta waves. They're extremely powerful. They kind of start at the back of your brain. They go like whoosh, whoosh, whoosh. And they go almost like 1 times a second or even slower. Now you may think 1 times a second, isn't that still very fast? No, no, no. For the brain activity, that's super, super slow. So when you think about this delta activity, when you're in deep sleep, if I'm waking you up, which by the way is very, very hard for me to wake you up, I basically have to scream your name or have like very dangerous sounds in the vicinity for you to wake up. If you do wake up, you are very, very cranky. We call this a sleep inertia. And you may have experienced this once if you wake up from quite suddenly from loud noises that you feel extremely groggy. And it takes about, it can take up to an hour or for some people even longer to kind of get out of that particular state. Now, during this slow wave sleep, we see, your core body temperature gets cooler. Your heart rate is very slow. It's now at its slowest rate, blood pressure very low, respiration rate very low, and you're basically deep asleep. And then you kind of climb back up, like you can see it on the left part. You go back to stage two. You go back to not really to stage one, but you go into this other weird phenomena. Your brain activity kind of looks like you're awake. It looks like you have a lot of beta activity, but you're not awake. And there's something really weird happening because your eyes are moving back and forth like nuts. It's like, what's going on here? Like, why is biology creating all these kind of strange phenomena? And if I wake you up during this part of the sleep, we call this rapid eye movement or REM sleep. You'll usually tell all these kind of bizarre stories like, oh, I was on a skateboard and I was going down a hill and da 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 da, and this happened and that happened. So you have these weird narrative stories and experiences that you're sharing. It's very likely that if I wake you up during that period, that in other words, you will report a dream. So we also call this state dream sleep. There's other strange things happening. Whereas in the other stages of sleep, I still find muscle tonus. So your EMG, your myograms will still show me that your muscles are working. During REM sleep, you're paralyzed. Your alpha motor system, neural system is out. And so you're completely paralyzed during that. Not completely, your eye muscles and some of your ear stuff is still working, but most of your alpha motor neuron system is not working. Now, and then you go back into, stage two, stage three, and you kind of cycle in and out. And, you have this cycle that, is about every 90 minutes or so on average that you cycle in and out until you hit REM sleep. During the beginning of the night, as you can see in the image to the right, what you'll see is that you'll have more of that deep sleep. During the end of the night, you'll have more of that REM sleep. So usually when you wake up at the end of the night, if you do remember a dream, which most of the time you do not, if you do remember a dream, it's usually near the end of the night when you have that a lot of that dream sleep. So your dream isn't evenly. I also want to tell you guys that you may see this in textbooks, but the reality is that everybody has their own pattern of sleep. For some people, it's 90 minutes. For some people, it's 70 minutes. For some people, the cycle is 120 minutes. And it also differs, for example, depending on your own experience, how your day was the day before, but also, your age. If you're a newborn, so like the situation that Madeline and I are currently in with young kids, they sleep a lot. And a lot of that sleep is taken up by REM sleep, rapid eye movement sleep. And you can see the pattern, for example, on top, where a 1 week old infant or newborns or 1 year olds, they have a lot more REM sleep and they have a lot more of these shorter cycles. Um, as you go older into becoming children and adolescents, you see more of that average 90-minute cycling taking over. During adolescence and adulthood, you see also on the left that the recommended amount of sleep is about 8 or 9 hours a night, which is not typically what adolescents always tend to get. And we see if you sleep less than that recommended amount, usually what we see is that your performance is less optimal than what it could be, right? Um, and then if we look at old age, and just look at the image to the right, you see that as we get older, we tend to sleep less. Our REM sleep, or especially our non-REM sleep, is being reduced. And if you look at the image to the right, what you'll see as you get older is that very deep sleep that becomes very fragmented, becomes very, very little actually. And what you also start to see is you'll have these multiple awakenings during the night. So we tend to wake up more during the night as you grow older. Um, and so what's important again is that these are averages, and that for every individual, you may have your own different characteristics of how your sleep cycle works. But in general, this is sort of what we see. Now, what I want to do today is I want to mostly focus on, sleep and learning. I'm not going to talk much. I think the last time I spoke, I'm not exactly sure what I did. But I think for today, I'm going to repeat some of these things. And so I'll leave some more time for questions as well. I want to talk about some work that's been published that we've done about sleep and learning in college students, past work, some published, some not, about sleep and learning in the elderly, and then also sleep. And what we're currently focusing on, and what I'm very excited about, is a project that I'm starting on sleep and transfer of learning. So I'm just going to talk about these three things. Before I do, again, as Madeline mentioned, I'm at the Department of Educational Psychology. I have a lab, the Neurobiological Lab for Learning and Development. I have a website there. You're welcome to check us out. And we have several missions. So in a way, I'm a little bit of an odd duck in an education department, because what's a neuroscientist doing there? But we're really trying to bridge the fields of neuroscience, psychology, and education. What can we learn from a perspective that views humans as Homo sapiens, as animals, basically, organisms that, unlike a computer that can just think and operate and reason and and have these heuristics, we need to sleep. And sleep is a very biological function, a function of biological creatures, in a sense, and it has a particular characteristic. So that's why, as a lab, we're very interested in the role of sleep and how it affects learning. And so we do research in these areas. We also have an educational mission, and so this is why I actually love to talk to you guys and hopefully disseminate some of the work that we're doing that might be relevant to make you all better learners, and also community outreach that we're involved in. So let's talk about sleep and learning in college students. And so a couple of years ago, we did one of the most famous sleep questionnaires, the Pittsburgh Sleep Quality Index, the PSQI. We measured and had reports from over 500 undergraduate students here at Texas A&M to ask them about their sleep habits. We had a very ethnically and a degree-wise diverse sample from folks who were in the sciences, engineering, liberal arts, et cetera, et cetera, et cetera, to ask them about their sleep. And so we asked them several things, and I'm just going to show you a few of them. So this is the bedtime that they've had, and you'll see that most students go to bed around 11 to 12 a.m. But we also have 25% of students at Texas A&M go to bed after 1 a.m., for example. Now, this may or may not surprise you. But if you think about how long do they sleep, and also keep in mind that graph that I showed you earlier about the recommended amount of sleep, especially for young adults, is around 8 to 9 hours a night. And here, the numbers are like the following. The majority of students sleep only about 6 to 7 hours. And is about 20% of the students, they sleep 5 hours, 5 to 6 hours or less. And so this is, for sleep researchers, a reason for concern. This may mean that a lot of students here at Texas A&M, they may not be at their optimal selves, especially when it comes to learning. Now, how well do they think they sleep? So if you ask them about their sleep quality, most of them say, well, I sleep fairly good. But, we still have a fifth who report that they sleep bad or very bad. So the obvious question about learning is there, what did we find a relationship between, for example, the sleep quality, the sleep duration, and uh, their grade point averages? And yes, we did. And this was just a quick analysis here, but I'm not sure if any of you are having done research or having a research background, but normally you don't find these really strong effect sizes and such linear relationships if you correlate in survey research. Usually it's way murkier. In this case, GPA, self-reported GPA is on the y-axis, and we see their sleep quality, for example, on the x-axis. And you can see people who report to sleep very poorly are having a very low GPA, and people who are sleeping well reporting a high GPA. This obviously is correlational work, but there's also quite a bit of experimental work that sort of confirms and also has a more mechanistic explanation for why there might be such a strong relationship between sleep and learning and doing well on exams. And so in studies where they sleep deprive people, where they have groups and you have a control group, an experimental group, an experimental group does not get sleep, and the control group just, goes to sleep. Once you put them in a scanner, once they've learned something, and you look at a particular area of the brain called the hippocampus, which we know is involved in memory retention, what we see is that not only do we see a 40% reduction in learning ability in terms of your ability to remember things that you've learned them before you had a bad night of sleep. What we also see is that correlates directly with your hippocampal activity. In other words, the brain structures that are involved in you encoding new information, taking up information, are basically almost offline, right? On average. And so you are way worse in taking in new information. What's also interesting and what we're also learning is that not only is sleep important for the encoding, the taking in of new information, sleep is also very important for the consolidation of information. So for example, suppose that I'm learning to play the guitar and I'm learning all sorts of new string combinations. If I don't sleep well the night after I learn this ability, I will not retain the information as well as if I did have a good night. In other words, we need to sleep well before in order to take in new information, but we also need to sleep well after to consolidate that information more effectively in our brains. And so, yeah, you may all have had the experience when you were younger or and you're cramming for an exam, and then you have your exam, and then 2 days later or one day later, you forget everything that you've ever learned. And that is also related to this ability of the brain to store information that you learn into long-term memory. And this is what the hippocampus is for. It stores that information into long-term memory. And so sleep is actually quite critical for effective learning and information. So we've also wondered about what are some of the reasons for some of these short sleep durations that we're seeing in college students. And so in a follow-up study, oops, I see somebody else is sharing their screen. Hold on. Are you guys still seeing my screen or not? No, right. Let me, okay. Am I back? Can you
Yes,
guys?
you're back.
All right. Here we go. And so one of the things in a follow-up study, what we did is we asked the students um, about cell phone use. And perhaps that could be a part of the explanation of why some of the students report poor sleep. And we had a couple of hypotheses about that. So why could nighttime cell phone use be poor for sleeping? The first one would be the blue light hypothesis. And so as you may or may not know, we have a particular circadian rhythm And there's certain side gabers that indicate for our bodies that it's kind of time to be active and time to be more sleepy. And this circadian rhythm, is activated by a set of hormones, including melatonin, for example. And we can see, for example, that if you have a lot of light intake, particularly in the blue light spectrum, which is what cell phones also emit, that may reset your melatonin and or suppress it basically, so that it messes up your circadian rhythm. And your circadian rhythm, your body basically tells you, oh, we're still during the day and you're going to be still active. And so that might be one of the explanations. Another explanation is the displacement hypothesis, and that is the idea is that people are staying awake. If you're awake and you're staying awake in your bed and you're watching your cell phone, for some, you start to, especially if you start to do work or socializing, you start to associate your bedroom psychologically with work instead of sleep. And a lot of folks who are suffering from insomnia, one of the most common treatments for insomnia is cognitive behavioral therapy, CBT. And one of the things they do for people with insomnia is, in most of the cases, they try to associate the bedroom with sleep. So don't do anything in your bedroom other than sleep. And these things work at a more Pavlovian sense. So they work on behaviorist principles. They go almost through unconscious routes. It's a form of implicit learning that you kind of activate when you are having these kinds of behaviors, if you're not associating your bed, for example, with sleep. And so the other one is the arousal hypothesis. And this is the idea that, when you're on your cell phone, you have increased emotional arousal that suppresses sleep. And, one of the explanations for that is that, your cortisol levels, which cortisol is a stress hormone, which is very good. We need that. And it also keeps you awake and vigilant, and it's tightly connected with hormones that are related to your circadian rhythm. It's actually so strongly related that people mostly fall asleep when their cortisol levels in the evening are at their very lowest. Now, what we oftentimes suspect is that if you're on your cell phone, and particularly if you're watching emotional content, for example, you have a particular love interest that you're texting with, and oh my God, he's not writing back, or she said this and it could be interpreted in that way, or, it may affect your ability to fall asleep. You'll get a bit of a cortisol joust from that, and that also can affect your particular rhythm and your ability to fall asleep. And so this is called the, arousal hypothesis of cell phones and sleep. And some of her findings were, so students who did not use cell phones in bed before sleeping, they were able to fall about sleep sooner, and they slept longer. These were relatively large effects, medium-sized effects, but it's pretty good. Students who watched emotionally arousing content before bed, they also showed increasing sleep difficulties and reported slow to sleep shorter. And so these are data that kind of confirmed some of our hypotheses that we had about cell phone use and sleep. In other words, I'm not necessarily recommending don't use your cell phone before sleep, but at least make sure that if you do use your cell phone, that you kind of avoid some of that social media that may be upsetting. The same way, myself, I have a bit of a rule with my wife to not have difficult discussions right before bed, right? And sometimes my wife has a tendency to talk about finances before we go to sleep, which isn't very conducive oftentimes to sleep. The other thing I want to talk about is sleep and learning in the elderly, and this is work we've done in collaboration with CTRL, the Center for Translational Research in Aging and Longevity, work with Mick Deutsch and Marielle Engel here at Texas A&M. And they have sleep facilities. They did not have a PSG, so I have my PSG over there, so we can kind of combine our forces. And they're very interested in aging, obviously, as the name of their institute suggests. And so we started a collaboration. But before we did, um, we were thinking deeply about why is it that we sleep? And one of the reasons that we sleep might be have to do with that picture you see on the right. This is your lymphatic system, and you may know that your lymphatic system is basically a system that cleans out a lot of waste products and toxins from your body. Um, but if you look very closely, if you look where the lymphatic system is, you may also look and find where it is not. And there's no lymphatic system in your brain. And there might be a very good reason for that. If you have a lot of that garbage collection, all these toxins flowing around in your brain and being transported here in and out through your lymphatic system, and that all circulates and mixes, that might set off this really tight balance, delicate balance of biochemicals that you have in your brain. Your brain has to be your central nervous system, so it has to be tightly regulated. And there's not for good reason. We have something called a blood-brain barrier, right? That stops a lot of uh, foods and particles from entering our central nervous system. And so one of the more recent theory is of sleep is that sleep is basically a solution to this particular design problem. It's it's a the brain has evolved a mechanism or nervous systems because it's not just our brains. It is basically even flies have a form that looks like sleeping, or every sort of creature that has a nervous system has a similar kind of mechanism. So the brain has come up with a solution to get rid of its metabolic products. So you may or may not know, but the brain is basically, in terms of its weight, it weighs about 2 pounds. It may be less than 5 or 2% of your total weight. But in terms of the energy that your brain takes up, it's more than 25% of your total energy. If you are very busy, if you're thinking very hard, or you're in a chess match, you may use your brain may use up to 50% of the total oxygen of your body, right? More than your muscles or your heart. So think about that. So think also about all the waste products and metabolites that it costs that are floating about in your brain. And during sleep, basically your brain has to clear these waste products. Now you may know these waste products. You may have heard of some of them like amyloid betas or tau. These are some of these waste products. And what happens during that time, it's almost like your brain cells shrink a little bit. And these waste products are being put into your cerebral spinal fluids, from which they're then put into your bloodstream and moved outside of your brain. And so during this phase, this is mostly occurring during your slow wave sleep. So when you're in that deep sleep. Now, when I mentioned these metabolites, such as amyloid beta and tau, you may have remembered a connection with Alzheimer's disease. And so what we were very interested in was not so much Alzheimer's disease, but a condition called mild cognitive impairment. And this is a diagnosis. This is a condition identified mostly by memory complaints. Sleep disturbances are among the core symptoms. And here's the interesting thing: the conversion rates are ranging from 60 to 100% to Alzheimer's disease in 5 to 10 years. And so these kind of memory deficits that you often see in elderly populations almost always result in a form of Alzheimer's disease. And so what we did is we collected data from 21 MCI patients and healthy adults. And we had a couple of research questions. And so we were wondering about how they sleep, and if their sleep may be related to some of their cognitive complaints. And so would they report poor sleep, but also what about their objective sleep quality? So if I were to put them in my sleep machine, what would I basically see in terms of their neural activity, and how does it compare to healthy controls? And so we did a lot of tests, a lot of questionnaires. We had them come in twice, first to get used to the sleeping area, And then, we did the real tests. We did several executive function tests, like a Stroop task, trail making task, and other kinds of memory tasks. We did some blood sampling too, and all of these things. So a ton of measures. And one of the tasks that I thought was pretty cool was the following task. This was a collaboration with University of Oxford, UK. It's called the What is Where memory task. And you have these weird fractal figures. And then individuals are either seeing one or three of these objects. And then there's a short delay, and then they see two of these figures, and they have to first indicate whether they saw the one that they saw before, right? Is there one of the images that appeared before? But then they also have to drag them to the remembered location. So it's quite a difficult task in a way. And the more we can also measure how precise they're able to drag them to that particular location as an index of visual spatial memory instead of recognition as well. And so what we found with this condition is that the MCI patients showed impairments on measures of identification performance, but they were mostly strongest when it was in the high load condition, when we were looking at three items, when they had to remember three of those figures, and as well as for the localization performance, which was largely consistent with what we're finding in the literature as well. Now, we were also asking them about their subjective sleep. So we were simply asking them the same questions we asked those college students. How did you guys sleep? How long do you sleep? What's the quality of your sleep? This is self-report. And here we found something surprising, and we didn't really expect to find this, but we basically didn't find any statistically significant differences between the MCI and the healthy control patients, which some people have also found, but some others also could confirm in the literature. And so this was sort of like, uh-oh. So, our hypothesis was that maybe part of MCI and perhaps part of how we can explain Alzheimer's disease may be related to sleep, but they don't seem to report any differences in their sleep quality. And so when we had our subjects hooked up to our sleep machine and actually looked at the neural indicators, we did find differences. And so here we found differences in slow wave sleep, just as we would predict it. The MCI patients had reduced slow wave sleep. They actually had a pattern where they had reduced slow wave sleep, and they compensated for it by having more of that less deeper stage 1 and 2 sleep, for example, but also was statistically significantly different between the control group and the MCI group, was the amount of sleep spindles that they've shown, where the control group, the healthy participants, had more of those sleep spindles, which, if you may remember from what I talked about earlier, are also related to memory function. And so this is what we found. So for us, we're currently writing this up and submitting it for publication. And so for us, what was really interesting actually is to find out that these physiological measures of sleep quality are actually better discriminate and maybe also relate more to particular deficits in MCI patients than, for example, their self-report. What we're finding, for example, was that slow wave sleep correlated, for example, with the high load condition of that task that I showed you. And so the folks who had better slow wave sleep, they also did better on that particular visual spatial memory task as such, also showing that relationship. Now, what we're working on right now and hoping to do in the future is about sleep and transfer. And before I start talking about that, um, I want to tell you about the study that kind of inspired us to kind of do that. And so a lot of my work has been in cognitive training. How can we become better learners? Can we train, for example, executive functions? Can I increase my working memory? And I've done a lot of work on that back at the University of Toronto and here at Texas A&M. And a lot of my findings basically showed that it didn't help, especially computerized training. And the reason it didn't help is so much because if you train your working memory, you will get better at the tasks that you trained, but they won't transfer to other abilities. In other words, if you do a game that will purport to increase your working memory, like Lumosity or Cogmet, and I hope maybe some of you are involved with those. If you play some of these games, you'll get better at those games, but it won't make you better at remembering phone numbers, or it doesn't work. So what happens is there is very little transfer happening. So this for me was very interesting. And so my lab is studying right now is how can we actually how can we increase transfer of learning? And I came across this study by Robert Stickgold, and this is the numeric number reduction task, and it's a very frustrating task for participants to do. So if the number is the same, you write down the same number. If it's different, you write down the remaining, and then you have to come up with the last number. So for example, if it's 1 and 1, then the number is 1. If it's 1 and 4, the remaining number is 9. If it's 9 and 4, the remaining number is 1. If it's 1 and 9, then the remaining number is 4. Then there's 4 and 4, so it's the same, then it's 4. Oh, you get a headache doing this. We're asking participants to do this for, hours at times. And here's what's interesting. There is a secret to this particular game that they're playing, these kind of puzzles. And it is that the final answer, the 9, for example, or whatever it ends up being, is always the second one in the row. Now, this is a bit of a hack, and you need to have some out-of-the-box thinking to kind of come up with that. And so what's interesting is if you bring subjects back 12 hours later to do the task again, but you deprive half of the subjects of sleep, you see a big difference in terms of their performance. The individuals who remained awake performed worse in discovering the secret hidden trick than the individuals who were sleeping. In other words, what happens during sleep might be more than just restoration and, prevention of clearing out waste products and just remembering things that you've learned. What happens during sleep might also be more actively involved in our creativity and higher order thinking. And so this got us thinking about, transfer of learning. And so we're starting a research problem, to examine transfer of learning, hoping to find out whether sleep can help transfer knowledge. So for example, here's an example. If you teach kids like 5 times 2 is 10, you could say, if you ask them on a test, what is 5 times 2? They may say 10. And it may be recognition memory, right? There may not be any transfer of knowledge. If they're able to apply this knowledge, if they've learned and understood 5 times 2, and then they also know how to understand what 5 times 3 is, therefore, it shows some transfer of knowledge with what they've learned. They've seen a deeper pattern in the mathematical equations that they've seen. And so I would call this, for example, near transfer. It's pretty close to what they've learned, but it's still a little bit new. Now, far transfer may be something like, what if I ask them a question? Oh, what if Mary is on a lemon stand and she's trying to sell lemons and she sells them for $1 a piece and she sold 5? How many lemons did she sell? How much money did she make? Same thing, but in a word for, and I would call that far transfer. Are you able to apply what you learn in school, or are you able to apply, what you learn in the classroom into real life kinds of or different kind of contexts? And so that's what we're currently testing to see whether sleeping and good sleeping has a function, has an important function in the transfer of knowledge. And so that's all I have for today. I think I made really good time. I planned to talk about for 45 minutes. So, and I'd like to open it to any sort of questions. And I'm not sure how this is going to work, Madeline, if you're going to collect some, or
Sure,
I
I
can I
certainly
can pick
can.
ones that I know the answers to, or
Yeah, we had one that did come through the chat, which is I've heard that environment, like the room temperature, the light, can affect your state of sleep. Are these actual factors that influence sleep?
yeah, these are actual real factors that are sleep. And so when you think about sleep, the first thing is about light, right? And so there are a couple of things that are important for making you feel sleepy in your body. There's a chemical called adenosine. And when you wake up, slowly adenosine builds up across the day. And then in the evening, the buildup of adenosine, we call that sleep pressure, is so high that you start to get sleepy. And then, normally when adenosine is at its highest, you sleep. And when you sleep, you have these adenosine is being removed from your brain and you wake up refreshed again in the morning. You have another process that's your circadian rhythm, your melatonin and other kinds of issues that sort of that are activated and influenced by your light input that make your body give cues to your body whether your body should be awake or should be asleep. And so your circadian rhythm is such that, it's very much higher in the morning, and it kind of slows down is in the evening when darkness starts to fall. And so these things kind of work independently. And if your adenosine levels and your circadian rhythm are sort of in synchrony, in other words, if your adenosine level, your sleep pressure is sort of high, and you also keep light reduction, you kind of fall asleep more naturally. And so this is very useful. And so one of the things you can do that our natural sleep cycle is such that if you wake up in the morning and you expose yourself to lots of light, you basically are giving your circadian rhythm a signal like, hey, the day's starting. And what you can also do if you have difficulty sleeping is, before you go to bed, even starting a few hours before bed, start avoiding, some of the high light sources, for example, that you look directly into. And that may make your circadian rhythm be more naturally in sync with your adenosine levels, so you naturally fall asleep more easily. And so there's two things you can do, right? So you in the morning, make sure you get some good daylight. There's almost no substitute for daylight. It's extremely light. It's much better. It's very different from having a little night light or being indoors and having artificial light. Artificial light is not as light as daylight. And naturally, we need a lot of that light. And so if you have difficulties, if you often feel groggy, you're not as productive, one aspect might be, yes, indeed, to look at light, and that might be exposing yourself to more lights in the morning if you can have a morning walk, for example. And the other thing you can do is making sure that you avoid lights, including perhaps the lights from your cell phone at night, so that you may fall asleep. You may fall asleep easier. Another, and this is more empirically shown as well, is that, when you are falling asleep, especially when you go into these sleep phases, temperature does seem to be very important. And so while you're sleeping, you kind of reduce the temperature in your core, your body. And a lot of that warmth is going to your extremities. And the cooler you are, the easier it is to fall asleep. And so sometimes sleep researchers recommend if you have to put your air conditioning on. I know people think 68 is a too cold, but that's sometimes what a lot of sleep researchers kind of recommend to use.
Mm.
Um, it's very counterintuitive. Sometimes people ask me like what about when I tend to sleep better when I take a hot bath. And after I've taken a hot bath, I go to bed, I actually sleep better, but then I'm warming myself up. But the trick is with a warm bath, what you're actually doing with a warm bath is that when you take a warm bath, your extremities, your peripheral nervous system gets very warm. It puts the blood out of your core. So in effect, you're actually cooling the inside of your body and making it easier to sleep that way.
Oh, wonderful. I was just thinking, I was like, that's probably why my little guy sleeps better when he has a bath before we go to bed.
Yeah.
So the next question is, do melatonin supplements really help you sleep?
Do what cell up
The
melatonin?
melatonin supplements?
Good question. I have to be a little bit careful about supplements and what I say and stuff because that research is not always very clear, but they do not help you maintain or necessarily sleep better. What they do is sort of like put your circadian rhythm into gear and giving your body the signal, hey, now it's kind of time to sleep. And so it's very good for jet lag. It's very good for if your circadian rhythm, for example, is off. But if you actually have an episode of insomnia, you're really not sleeping well, you're waking up regularly in the middle of the night, or you can't go to sleep, um, um, and oftentimes that may have different reasons. Melatonin is actually not that effective. It usually can't hurt, so it doesn't have a lot of addictive properties or something like that. So if it's something that you can put on the list to kind of try if you have difficulty with sleeping.
Excellent. So the next two questions are related, and they are about using fitness trackers to track your sleep habits. One is their research that shows or discusses sort of the accuracy of those, and then is there perhaps one tracker that is better than another?
So I'm not observe. I cannot speak for all trackers because the last time I looked into it was more thoroughly was maybe 2 years ago, and I know a lot. They're working on a lot of trackers that might help. So a lot of the fitness trackers work on the principle of, for example, you can even do this with your phone because your phone has sort of like motion detection in it. You put them on your pillow or under your pillow, and basically what it does, it no starts to notice that when you are in REM sleep, and you may remember that I told you during REM sleep, your alpha motor neuron system is paralyzed. And so basically, you stop turning and twisting, and your motor tonus is very low. And so your phone is picking up zero movement. And this is how your phone thinks or estimates that you are, for example, during REM sleep. In the other phases, you are in non-REM sleep, but you can already think you cannot really make a distinction between um, stage one sleep, stage two sleep, or stage three sleep. And so that's what a lot of these devices cannot do. And their reliability compared to, a Ph.D, a polysomnograph, what I have, just isn't comparable yet. So if you have severe sleep problems or you really seriously need to look into it, the best thing for now is still to come into an actual sleep lab for treatment. Um, will this happen? Yes, for sure. So I'm a person, for those of you who know me, I've worked with companies and have often have found some difficulty with a lot of companies are more motivated by selling a product and they're not so much interested in that it actually works or not. It's more about, well, I need to make their money. Their motive is profit related. And oftentimes they take a short-term perspective. And that doesn't always make it easy for a researcher like myself who's more interested in, does it actually work? Like I want to know from a truth perspective, is this something really valuable? And yeah, a lot of the track devices that I've worked with, wearable devices, I'm quite skeptical of. However, if there is a device that can actually target sleep activity during using actual neural activity, sleep will be one of the first things to come. And I know that there are good professors working with companies right now. And hopefully in the next 2 years, we're going to have devices that can reliably, almost as reliable with 98% congruence with a PSG to measure your sleep activity. And that will be, that will be very important. That will be a game changer in a sense. And that will allow you to more reliably index the degree of slow wave sleep and stage two and stage one. And the reason I believe this is feasible is because those brain waves are so powerful. They are, you don't need 20 electrodes. You just need one or two
Mhm.
electrodes here on your scalp, and you'll be able to pick up these frequencies quite reliably. And so I have no doubt that there will be very good, reliable devices, if they're not already out there, and I may have to look again, but as far as I'm concerned, they will be there very soon.
That's very exciting.
Can I say
Is
one
it,
more thing?
yeah, absolutely.
What will also be in the future, and there is research experimentally now, um, still a little bit wishy-washy, but it sounds like it's going to be working, is sort of an induction of electricity. So suppose that you have a device or a helmet that you can wear that will electrocute you very, very mildly, but it does so at particular frequencies. So they've discovered that if you mimic the neural frequency that of slow wave sleep in the human brain, like for example, that's 1 times or 0.75 times per second, you electrocute at exactly that pace, not higher, not lower, because they've tried both, you will actually increase your learning potential. This is not science fiction. So this actually works. And so it looks like it has an effect that sustains slow wave sleep longer, whereby you also get some more of those beneficial effects. And if you can tailor those frequencies in that helmet, for example, to exactly the kind of frequency that you yourself sleep in your slow wave sleep, and that may be different for everyone, right? That those are not all the same. The benefits were even stronger. So I also predict that probably within, and this is maybe something in the next 5 years, we may be able to see devices that can enhance learning through, or basically, and really enhance more deep sleep with, and have confer a lot of the benefits of having deep sleep using those particular devices. So,
That's exciting. I'm trying to maximize my sleep however I can. I have a question that came in to me privately that says, they've heard that there are higher chances for people with neurodiversity, such as autism, and that neurodiversity increasing the chance of sleep disorders. Is there research on that? Could you speak to that at all?
I am not familiar with those very much specific cases. However, if you look at sleep disorders, and you look at, for example, the field of psychopathology and neurodivergent individuals, there isn't a condition that I know of that is where sleep is not affected. So you
Mm.
see it in ADHD, you see it in autism, you see it in schizophrenia. It manifests itself in a different way. And this is an area where I tell my students who take my classes, if you guys want to study something and you want to have a job and we need more data on something, this is the field you need to get into, because there's still a lot we do not yet understand how sleep interacts with all different kinds of psychopathology. And so, for example, a good example is, for example, addictive behaviors related to alcohol abuse. We know, for example, that alcohol abuse is a REM sleep blocker. In other words, if you drink too much alcohol, you may not get it, you may suppress the amount of REM sleep that you get, but your brain needs an amount of REM sleep. And in fact, it will have something that we call REM sleep pressure. And that kind of pressure kind of keeps building up. If you keep drinking alcohol and you keep depriving yourself of REM sleep, you may get psychotic symptoms. You may get hallucinations, which we now think may be actually a form of dream seeping into your waking life. This is a bit of another way of trying to understand hallucinations or psychotic episodes by having a perspective that includes an understanding of sleep, for example.
Very interesting. I think we have time for one more question, which kind of it connects to what you were just speaking about. But for individuals who might be on prescription sleeping pills like Lunesta or Ambien, are they still able to get to that REM sleep and that recovery sleep?
So with a lot of the more classic medicines that are used for sleep, like the benzodiazepines and like Ambien and such, for sleep researchers, again, I'm not a doctor, so don't take this, but this is more from from a scientific perspective, looking at these kinds of studies. Ambien, for example, these things are sedatives. They don't make you sleep better. In fact, if you look at brain activity, particularly slow wave sleep, and you look at what happens during your slow wave sleeps during Ambien, the waves aren't as deep and as powerful as they should be. In fact, Ambien it doesn't really help with your sleep. It mostly, you have a more attenuated, different form of slow wave sleep that isn't really the same and isn't as powerful, it seems. And so I think that also in the future, hopefully what we're going to see is sleep medicine medication that will do a better job at creating also a neural pattern that creates sleep. So a lot of classical sleep medicines have worked under the assumption that if you just are in bed longer because you take this medicine, you sleep better. In fact, being in bed longer is sleeping. Being unconscious is sleeping. And, if you do the research and you look, for example, at that brain activity, we know that sleep is this delicate dance with all these cycles and different stages that you kind of have to go through that have their own unique kind of functions that relate to experience during the day. Sedatives, are, are basically not the most optimal ways of dealing with sleep, but also hope and that in the future there will be medication. And I think there are some medications already on the market that are better for dealing with sleep.
Thank you so much, Dr. Woltering, for being here and sharing this information with us. I hope that we all found it. I know I found it beneficial. I hope everyone else did too. If you are interested in continuing the sleep series with us as a participant, our next session will be next week, and we'll be talking about mindfulness meditation and how that can associate with your sleep as well. So I will stay on for just a little bit if anybody has any living well questions that they might want to ask. And again, thank you so much, Dr. Woltering, for being here with us today.
You're welcome. Thank you all.
Yay. Everybody have a wonderful afternoon.